Welcome. In this lecture in linear data analysis, which has multiple sessions, we'll explore how to use one matrix to approximate another matrix. The main concepts in this lecture are we'll look at the axioms of matrix norms, and we'll look at two norms in particular. These are commonly called the L2 norm and the Frobenius norm. We'll look at how to approximate a matrix using a rank 1 matrix and then using a rank k matrix. One problem that we think of as we go through this lecture is how can we approximate the column space of a matrix? Well, to do these approximations, we need to have a way to measure two matrices, and this is done by using a norm that's an extension of the idea that we have from vector spaces. So the question that we want to answer is, if we have two matrices, how close are they? That is, how can we measure the difference between two matrices? Well, let's suppose that we have two matrices and they both have entries that are all real numbers and the matrices have the same size. And then let's also suppose that we have some other number alpha that's a real number. Well, a matrix norm has to satisfy four axioms. The first is that the norm has to be non-negative. The second is the norm has to be zero if and only if the matrix has zero in every entry. The third axiom is that if we multiply a matrix by a real number, that is equal to the absolute value of that real number times the norm of the matrix. So these are all fairly straightforward extensions of vectors. And a fourth one is also an extension, and it's called the triangle inequality. And in vectors, the notion of triangle makes sense. In matrices, it is simply called the triangle inequality. And what it says is that if you add two matrices and you take the norm of that sum, that an upper bound on that is the sum of the norms of the individual matrices. If a matrix norm and a vector norm are compatible, this is a technical term, what it means is that for any vector that can be transformed by the matrix, that an upper bound on the transformation of that vector by the matrix is the product of the vector norm of the vector and the matrix norm of the matrix that we're examining.